So welcome back after the long break. So in October, in the last lecture, we looked at El-Gamal signatures. So I should go a few slides back. So a very clever way to take Diffie-Hellman and turn it into a signature scheme, which is something that happened more or less 10 years after Diffie-Hellman was invented. And then, quite surprisingly, in '94, so this is when cryptography finally started to take off, because computers became faster, the World Wide Web was there, and the US government pushed a different standard than RSA or El-Gamal. They proposed DSA. DSA is very similar to El-Gamal, but instead of working modulo prime, you work modulo a prime where p minus 1 is a large prime factor q, and you work in a subgroup, a smaller set of numbers, mod q. So you can see this here on the slide. And so at that time, p was 512 bits, 768 bits. Today, p should be 2,000 or 3,000 bits. But q can be, at that time was 160 bits, today can be 256 bits. So it's actually very nice because your signature R and S is much smaller. So instead of having 2 times the size of p, which today would be 4,000 bits, 2 times the size of q would be 512 bits. So it's actually has some nice features. It's a bit more complex, so I will not go through all the math, but more or less the principles of the mathematics are the same thing. So you cook up this clever equation, which you can then verify only with public parameters. And a big disadvantage for the US government was that with RSA you could sign and you could also encrypt. With El-Gamal, well, you could turn it easily into a Diffie-Hellman scheme, an encryption scheme. They actually made DSA so you can't encrypt with it. So in fact, it was less functional, but the US government found that a great idea. So as I said, the DSA has much shorter signatures. It also specifies very specifically how you have to generate this random number k. Okay, so when you type a signature, you make actually a new key pair. So you have your long-term key pair x and y is after the x. The first step of a signature for El-Gamal and DSA is to generate a random number. And actually DSA tells you how to do this, how to generate this random number. And it turns out that actually there was a flaw in there, which actually made you leak bits of your secret key. And so from a few thousand signatures, you could find back the secret key of the signer. This was pointed out by Bleichenbacher, and then they fixed that bug. But as you see, also the NSA makes serious bugs. And then El-Gamal does require a few checks. So if the parameters are set up maliciously, then El-Gamal is insecure. And as I said, El-Gamal is more functional. It's more suitable because you can use it for encryption as well. But the US government had quite a different view of this. They saw this as a disadvantage. So El-Gamal is no longer used. DSA is also no longer used. What people use today is the elliptic curve variant of DSA called ECDSA. And there is actually a version which has some clever algebraic improvements called EDDSA, DSA, using Edwards curves. And this is, for example, what's being used in signatures in Bitcoin or in many cryptocurrencies. So this is why I show this to you. You don't have, of course, we don't dive into elliptic curves. We don't dive into the details of DSA, but I show it to you because it's actually a very important signature scheme. So DSA versus RSA, so discrete log of factoring is equivalent. If you go for elliptic curves, of course the key lengths, so discrete log in elliptic curves are much smaller, but DSA has the advantage that it operates mod Q if you work modulo prime, which gives shorter signatures, and the R can be pre-computed. But as I said, you can't use DSA for encryption. And then in RSA, people like RSA a lot, and we will miss it dearly once it disappeared for post-quantum algorithms, because in RSA, verification is raising to the power 3. Okay? This is a cubing. This is a very simple operation, just a squaring and a multiply. While if you look at the DSA equations, you see that you need several full exponentiations. So in DSA, verifying is more expensive than signing. In RSA, signing is more expensive than verifying. But if you look at it in the real world, for example, Microsoft signs a code update, Microsoft has to sign once, and then a billion of PCs have to check it. So in fact, for most signatures, you put them only once, but you check them billions of times. So in fact, you want the verification to be faster than the signing. But DSA has the opposite. So that's a big advantage of RSA. There was also, this is a long time ago, there was very big fights about patents, and a lot of energy has been wasted on this. But this is now a story of the past because the RSA patent expired 22 years ago and the DSA patent expired 12 years ago. That was a very big issue as well in the past. And so as I mentioned, DSA has an elliptic curve variant, which even shorter keys and shorter parameters. And there is even a new variant called EDDSA that's even more efficient and has certain advantages. So as we looked at in the second lecture, we now need post-quantum schemes. So NIST has announced about a year and a half ago that there would be new schemes. Dilithium is lattice-based. The draft standard was published a few weeks ago in September. There is also Falcon. Falcon is very nice because it has 4 times shorter signatures. So a Falcon signature is about 600 bytes. A dilithium signature is 2,000 bytes. And an RSA signature is like 200 bytes. And an EDDSA signature is something like 40 or 60 bytes. So the only problem with Falcon is that nobody understands how it works. So it was 6 years in the competition, and they said it's a winner. But now they realize that they can't describe it, so they're still figuring out how to write a standard because they don't understand how it works. So very interesting to see what's going to happen there. And after 6 years, NIST has to admit that they can't make a standard because they selected an algorithm which they don't know actually how it works. It uses floating point algorithm, so if you have floating point integers, this is great. If not, it's a misery. And then there is 2 IETF-based standards, LMS and XMSS. These are hash-based signatures. And then NIST added another one called Sphinx Plus, which is also hash-based. It's more complex, but LMS and XMSS are stateful, which means you have to remember how many messages you signed, and if you forget, your security is broken. In Sphinx, you don't have this problem, but then Sphinx signatures are like 100 times bigger. So you pay a very big price for the more security. So, and also NIST was not happy with this set of algorithms. So they actually did a new call, and in last June, 40 algorithms were submitted. Some of them are a bit more efficient and a bit more compact. But so I think we will have to wait another 3 years before these standards will be ready. So this is still an area very much in flux. I think what the world is doing is going to dilithium. The NSA actually likes dilithium, LMS, and XMSS, and they don't like the other ones. I don't know why, but that's the NSA. Just to wrap up, so in public key versus secret key, so we can have agreement of a secret over an open channel, and we don't have a central database with all the keys like in GSM or like in your bank. So your bank has somewhere a database with all the keys of the users, and if this database is compromised, they're in trouble. And with signatures, with public key, you can sign stuff, which is very important for code updates or for open systems in general, where you don't have a prior relationship. Sender and receiver have a different capability, and a third party can resolve disputes. By the way, there is some very interesting developments. I can't digress too much, but I've spent the last few weeks again on politics. So Europe, in 1999, they made an electronic signature directive, more or less saying that if you sign digitally, it should be equivalent to signatures on paper, if certain rules are followed. And then they realized that, of course, the Belgian ID card and the Estonian ID card, they don't talk to each other. And if you go to any other EU country and you offer a Belgian signature, good luck, they will not recognize it. So they made IDAS 2014 to actually harmonize these things and at least create an infrastructure to solve this, but it was not good enough. Also, you should understand that there is only 2 countries in Europe that really have identity cards for everybody, which is Estonia and Belgium. In all the other countries, it's optional, and most people don't have it. In Austria, it's quite widely used, even if it's optional, but for example, the Netherlands doesn't even have one. Germany, they have one nobody uses, and so on. So this is a big problem. So now Europe has made eIDAS 2 because they've seen in Corona that, in fact, you can roll out a mobile app in 6 months. And so now they said, oh, we're going to in 6 months roll out an identity app for everybody in Europe, which is, of course, a nightmare and a disaster. They made a regulation for this, so there will be national wallets that have your identity card, but also your driver's license, your study results, everything will be in there. Of course, it's a privacy nightmare because everything will be now centralized. And what Europe wants is that every time you go on the internet, you have to use this wallet and they find out what everybody's doing. So researchers lobbied for unlinkability mechanisms for privacy, and this is now optional. So in fact, if one member state says we don't do privacy, then all the vendors will go there with their stuff, and then they can track you from there. And then the other thing, which is even worse, but it's actually too early for the lecture. You better understand this in a month. But more or less, Europe has said all member states can issue certificates, and they have to be in all the browsers. So it means every browser has to trust every member state. It means member states, they can issue fake certificates for Google, so they can look at your conversations with Google or those with Meta or whatever they want. And the browsers, of course, they don't like this. They have if you want to be in their browsers with your keys, you actually have to go to a long vetting process, an audit. And so the member states say we can bypass this audit. We can just tell you to use it. And even if you detect that we misbehave, so we're trying to cheat our users, as a browser, you'll not be allowed to remove us. We have to give you the permission to remove you. And certain mechanisms to detect this misbehavior will be forbidden. So more or less, Europe is trying to create like a surveillance state. So you wrote an open letter, but the Commission more or less has ignored it. And I'm very curious, but I can't be there. So at 11, there is a press conference in which they will announce their solution. But I'm very skeptical what's going to happen. The other thing is that so they realize that what they do is really bad, so now they actually try to explain that, oh, but our certificates, they're only for identity and they don't do keys. But it's quite not how it works in browsers. Your identity is coupled to your public key, and if you can change the public key to a different identity, then you can read all communications. So more or less, what the risk is that in Europe we'll be able to encrypt, but only with a key that the government also has. And so this we'll see the result of the press conference. Also interesting, in Belgium, the press was not interested. The only one who published about this is Data News, Le Soir, and Het Belang van Limburg, but the other press was not interested in this story. It's too technical, it's too difficult. It's just mass surveillance of citizens, who cares, right? I mean. And so before we had the CSAM regulation checking for child porn, so they will put a checker on your device to look at all your photos and all your content. And before that, we had Cyber Resilience Act, which means as a software company, if you find a bug in your product, and even if you don't have a fix, you have to tell your national government. We can then start hacking all your customers, because you have to tell by law the bug, and then governments can actually hack your customers, and you can't defend them because you have to tell the government before you have a fix for your bug. So sometimes I'm very busy because I've become a half-time politician, but this is what it is, okay? So it's actually a very important point in society because more or less the internet was a bit of the Wild West, and then regulation is coming, but Europe claims to protect privacy and human values, but more or less what they're doing is under pressure of Europol, and some member states like Spain and France, they're making Europe a surveillance state. I mean, we're actually copying the Chinese model more or less. And we get worse than the US in this respect. Okay, so at least now you understand what's happening. Sorry for the digression. But so we do use signatures a lot, and for now they're not yet spoofed by governments with their own websites and their own keys. But so the big challenge, of course, will be the post-quantum migration. Okay, so then something about protocols. So far we've only talked about Alice and Bob sending messages to each other, or Alice and Bob storing information, or a transaction sent from Alice to Bob, or a software update. But in fact, you can do much more cool stuff with cryptography. And so in the 80s, people asked the question, what if Alice and Bob get divorced and they want to agree who gets the nice car and who gets the apartment at the seaside? And so, of course, the solution for this is Alice and Bob will meet and they flip a coin. But what if they don't want to meet anymore? but they're so angry with each other they don't want to meet anymore. So can they actually do coin flipping over the phone? Right? And so it's very simple. Alice says, okay, I'll take a coin. And it says to Bob, head or tails. And Bob says tails. And Alice flips the coin and said, oh, sorry, it's head. I can choose first. Okay? And that doesn't quite work. Maybe today with video chat, you could make it work. But still, would be a bit tricky. Because maybe Alice could flip 2 coins or something. But so the question is, can we do this over the phone without actually having video connection? And can we do this? We also look at sharing a secret between several people. This is very important because sites are hacked. And sometimes for example, if you have a lot of cryptocurrency or you're holding root keys for the DNS infrastructure, for the internet infrastructure, or for a CA, you don't want that one hack puts you out of business and somebody takes all your money or takes control of all your systems. So can you actually put your keys in multiple places in a clever way? You can do more clever things like playing poker over the phone or exchanging information. So assume that 2 governments want to share some double agents. So they discover both that some of the people are double agents. So they want to share the names. And so how can you do this? That you can, of course, send the first bit of the name and then the second bit. How can you be sure that you always get the correct bit? But if the one party stops, they only have 1 bit advantage. Okay. A lot of clever stuff was developed in the 80s. At that moment, there were still nuclear test ban treaties and disarmament treaties. As you know, we've all thrown them out of the door now. There is no more protection against nuclear weapon stockpiling, at least not between Russia and the US. So how to verify this stuff? Of course, e-cash, anonymous communications, things like Tor or a European wallet where you can actually have a different identity for every website you visit, these kind of things. This is all possible. The millionaires problem is a bit of a luxury problem. So you have 2 millionaires and they want to find out who's the richest, but they don't want to reveal how much they own. And you can do all this with cryptography. Auctions and so on and so on. So this is more or less all things we do. So I just show you 2 simple protocols. But in fact, there is a course on cryptographic protocols, follow up or in parallel with this course, where several of these protocols are discussed. And there is still a lot of research on doing more of this stuff. But so how can Alice and Bob agree on a coin flip or agree on a 0 or a 1? So they first agree on a function, so they use SHA-3 as a hash function. And then Alice will generate X. So she chooses a random input X. So you have 256 bits, and she hashes X. She computes Y is f of X. And she sends this to Bob. So the hash result, so we call this a commitment. So you choose a random value, and then you commit to it. You're bound to it by sending this value to Bob. And now Bob has to say, I think X is even or X is odd. So he has to guess 1 bit of X. Okay? So he says it's odd or even. And now Alice reveals X. And of course, both parties can check whether X is odd or even. And so Bob now can also check that f of X is indeed equal to Y. So he can hash X and check that it's equal to Y. And so now they can both agree who wins. So this is how you do this. Of course, we need some security. And so, of course, if Bob gets the parity correctly, the 0, then he wins. Otherwise, Alice wins. So, of course, you want 2 security problems. First, the commitment should be hiding, which means if Bob looks at Y, he shouldn't be able to tell anything about X. Right? So, more or less, looking at Y, it should not be possible to find out any information on the least significant bit of X. So if you could invert function f, you have a big problem, because then Bob can just invert, find X, and then know the least significant bit, and he can always win. But so in general, if f is a one-way function, then you can't do this. And of course, Alice, she has different ways to cheat. Alice could try to find X and X prime, where X is odd and X prime is even, or vice versa, and such that they have the same value f of X. In that case, of course, Alice can always win. She can make such a collision, as we call it. Then she can send f of X, and then depending on what Bob guesses, she can then release X or X prime. So if my hash function of my function f is collision resistant and actually not invertible, pre-image resistant, then this is a good protocol. So it's not such a hard problem to solve. You just need to assume the existence of one-wave functions and collision-resistant functions. So now, different problem, secret sharing. So this is information theoretic, so we can do this in such a way that even if the adversary has unlimited power, you can't break the scheme, a bit like the Vernam scheme. And so the problem is the following. You want to have a secret and divide it over n persons in such a way that we call it the threshold scheme. If you have t or more people, they can reconstruct the secret. But if you have less people, they have no idea about what the secret is. So what is the application? For example, I know a large financial institution in Belgium, and they have some CA, certification authority, where they sign certificates. And this is somewhere sitting in their basement, this important key. But what if the building would burn down? Or they would have a fire in the computer room, then they lose their key. So, well, of course, what you want to do is take a backup of that key and store it somewhere. But, this is a tricky business. Who are you going to give it to? The CEO of the company, but what if the CEO somehow gets bribed by the NSA or the CIA and then they lose his key? You can go to a notary public, and most notary publics are honest people, but maybe with a lot of money you can bribe them as well. So what they did is they divide their key in 5 pieces, and they actually gave it to 5 presidents or vice presidents of the company, so high-level people in the company. And each of them get a share and brings it to their choice of notary public. So it was actually 5 notary publics who each own a share of the key. And if a disaster happens, then even if one executive is traveling and the other one actually just left the company, they still have 3. With 3 people, they can still reconstruct the key. So they can go to notary public, ask for the key share, and then recompute the key and start up again. This is not new in the sense that, for example, in banks, now banks have level of cash, but in the past banks were also storing cash. It was always the case that not one person could have access to the money. So there were typically a safe with 2 keys, and you had the director plus some other person, so that if something happened to the director, there was a backup solution, but also if the director was corrupt, he couldn't empty the safe and then disappear with all the money overnight. So there was always, this is a very well-known mechanism in security. So this is used to store keys. I gave you the example of a financial institution, which I cannot name, but also, for example, the DNS keys, so the root keys that sign DNS, that secure DNS, that make the link between an IP address and a name. There are 9 root servers, and they also use this kind of mechanisms. So if you compromise a few of them, you still cannot attack DNS. So the easiest case is if you have t equal to n, which means that everybody has to be there to reconstruct. It's a bit risky, because then if somebody drops dead or some computer crashes, you can never find the secret back. But that's the easiest problem to solve. So your key is a 128-bit string, so V128. So what you do is, a bit surprising maybe, to the first n-1 participants, you just give a random string. You just generate them 128 random bits. And then the last participant, he gets a sum of all the random strings plus the real key. So you would first think this person has more information, but in fact what he gets is an encryption of the key with the one-time pad, in fact with n-1 one-time pad. So there is no information, in fact, on the key in this n share. But of course, if you rewrite this equation, the key is then the sum of all the shares. So if you XOR all the shares together, you actually can find the key again. This is not so difficult to see, but if you miss one share, in fact, you have no information, because what you get is the one-time pad encryption of the sum of the other shares, and the one-time pad is secure. So if you don't know that key, there is no way you can go back. So this is how it works. So it's very secure, but of course, if there is a problem with one party, then you'll never find the key back. So for example, if you have bitcoins, I wouldn't recommend this scheme, because if you put one key on one laptop and one somewhere in a safe and one on a mobile phone, and then the mobile phone dies, well, then all your bitcoins are gone. You can never find them back. So Shamir came up with a better scheme, and the idea is very simple, geometrically. What you do is you choose a random line in the plane, and you can imagine this is done with reals, but in practice we do this mod p, where p is a large prime. Well, large enough to contain the key, so at least 128 bits. And it turns out that you can calculate, if you did the preparation for public key, you can calculate mod p, right? You can calculate mod modulo prime, and you can add numbers, subtract numbers, multiply numbers, and you can divide except by 0 or a multiple of p. So in fact, more or less, what you can do with real numbers, you can do with integers mod p, but you only work now on 128-bit numbers. So it's much easier, more efficient, and you don't have problems with rounding and so on. So more or less what you do is very simple. So participant 1 gets the polynomial in 1, participant 2 gets polynomial in 2, and so on. Participant 6 gets polynomial in 6. And the key is the intersection with the y-axis. So in this case, you have a threshold of 2 and 6 participants. So there are 6 participants who each get a share. Now, if you have one participant, he knows, in fact, a point in the plane, but he doesn't know which the intersection is of this line because he doesn't know about this line, and there is actually many lines going to this point and intercepting the y-axis in all the kind of points. You can show that there is as many lines as there is intersection points. So more or less, with 1 point, you know nothing. But if, say, 1 and 4 get together, then they can reconstruct the line, and they can find the intersection point, and they can find the key. So it's very simple math. In this case, linear interpolation. In general, it's Lagrange interpolation you have to do, but this is just addition, multiplication, and division, and you can do this mod p. So here is what if you want t equal 3. So this is the scheme used by this financial institution. Then you need a parabola, right? You just have the parabola, which is defined. You choose a parabola, and then you make sure that the constant term of the parabola is the intersection with the y-axis. And then you give everybody their point, and now you need 3 points on the parabola to reconstruct the parabola, and then you can find the intersection point. If you have only 2 points, you have no idea, again, what the value is. So this is now used by some cryptocurrencies, as I said, by some financial institutions to protect their keys. So here is the math. It looks very complex, but if you look at the pictures, it's very easy. So more or less, the secret is, say, a 128-bit string. You choose a prime that is at least 2 to the 128, and it has to be also bigger than n plus 1, the number of participants, but in general, this is the case. So what you do is you just pick t minus 1 random coefficients of your polynomial. Your polynomial is of degree t minus 1, and then such a polynomial is determined by t points, like polynomial of degree 1 determined by 2 points, by degree 2 by 3 points, and so on. And so you just pick random coefficients. So it doesn't matter. So they can be random integers between 0 and p minus 1. And then the constant term of the polynomial, this is the intersection with the y-axis, this is your key value. And so now you give to participant I the share qi. So you evaluate the polynomial in point I. And you calculate everything mod p. And so for reconstruction, you collect t shares. Then you just apply Lagrange interpolation. It's the same formula as for the reals. You just have to now divide over mod p. So you have to compute inverses mod p with Euclidean algorithm. But it's the same algorithm. And then you find the intersection point, and that gives you the key. And so if you have t minus 1 points, you have no idea. In fact, for every extra point you add, you get a different key value, and you don't know which one is correct. And once you have t values, you know there is a unique solution. Okay, so this is something that shows you can do more, also cryptography with multiple parties and multiple entities. And this is something I think is becoming more and more important because first we get cryptography everywhere, and we have also many more devices. On the other hand, we know that securing individual devices is very hard. So probably you want to have a clever way to hedge your bets, and I think it's a matter of time before we see these systems that, for example, you more or less put part of your key in your phone, part in a tablet, part in your laptop, part in your smartwatch, and then if 2 of those come together, you can actually get access to information or reconstruct data. It sounds like magic, but cryptography is in part magic, but the mathematics is very simple. So we did some experiments with this, and the main problem we found is that users don't understand this. So it's very hard to convince users that it's actually possible to lose 2 out of 5 devices and still find back your key. So this kind of, it's more, can we do this? Can we convince users this is happening? Okay. So now we move on to the first set of protocols, very simple protocol, entity authentication, very important because we have to identify ourselves all the time. So we look at the goals. We look at the strengths and limitations of passwords. Unfortunately, I still have to talk about passwords because more than 20 years ago, Bill Gates said this is the end of the password, but unfortunately, we still have more passwords, although we now finally see progress away from passwords. And then we look at some subtle problems in practice. So if you see where we're focusing on, if you remember this slide, we're looking at authentication of entities, which we should really call entity authentication. But I just want to warn you, cryptographers sometimes call this identification, while some other people call this claim identification is claiming a username rather than proving the username. So we look at the problem, look at passwords, look at challenge response protocols, and then look at biometrics, and then at special issues. The problem is very easy. You show up somewhere and you claim to be Alice. That can be you enter your bank, or you go to an ATM machine where you want to withdraw cash, or more or less, in fact, when you make a payment, very often today, a payment is authenticating yourself and proving you have money on your account, or of course you cross a border, or you log into a website. We do this many times every day. And so, of course, you can claim an identity, but why should Bob believe it's you? And so this is the definition of entity authentication, is that Bob, in this case the server, is convinced that he's talking to Alice and that Alice is alive and active. Okay, so you really want to know in entity authentication that Alice is really present at this moment and is not something that happened a year ago or 6 months ago. So at the ATM machine, they really want to know you're there at the moment the money comes out and that not somebody logged in there before. In general, authentication of entities has to do with a live interaction between two parties, and you really want to know this other party is there at this moment. I have a very macabre example of this to make sure you never forget that this is important. So about 10 years ago, there was a story in the press that in South Africa, a terrible crime had happened. So what happened, somebody had passed away, and so in South Africa, many people still can't read or write, but they can collect a pension, and to collect a pension, you go to the post office and you put your fingerprint on a document, and then you get your pension. Now, this person had passed away, but the relatives still wanted to collect the pension. Okay, so can you imagine what they did? They took the body in between them, they dragged it to the post office, they used his finger to get the money. So it's terrible, but so why did the protocol fail? Because the post office person didn't check liveliness. This person has to be there in person, right? Otherwise, it's useless. And I know it's not a very nice example, but hopefully it will make sure that you don't forget on the exam that authentication always involves liveliness. So the rule of thumb is you identify things on something you know, like your password or your PIN code, something you have, like you're authenticated in the university if you want to enter a computer room with this badge you have, or for your bank you use a smart card, or for your mobile phone you have the SIM card at this moment. And then more and more we see biometrics. So properties of your body are being used. Most smartphones you can now use your fingerprint or your face. This used to be very expensive. Biometrics was only for military systems and very expensive systems like financial sector where we're printing money. But today these sensors are so cheap that it's now widely used. We also switched to behavioral biometrics. This is not physical properties of you, but how you behave, how you hold your phone, how you type, how you walk. So this is now where biometry is heading. So try to observe the user in all the contexts and try to take all elements into account. It's not very privacy friendly, but this is more or less where we're going. And then finally, what is becoming more important also is location. So this was already very early on. So in the 80s, there were mainframes, and you could work at home by dialing up the mainframe. And then you had these modems giving you the blazing speeds of like 14,000 bits per second or so. But what happened was, in fact, To avoid attacks, you had to call the mainframe and then hang up, and then the mainframe would call you back. And this was good because then the company paid the phone bill, because at that time a phone call was very expensive, and a session of an hour could have cost easily 20 euros or so. But also it was an authentication mechanism. So they tried to use the phone network to localize things. Today we have, of course, GPS, but GSM as well. GSM, I mean, many crimes are now solved based on your GSM data because they know where everybody is. So if they run special protocols, they know where you are within a few meters. But we also have GPS, Galileo, GLONASS, Paidu. So we have now all these satellites hanging above us, and it's possible to find out where we are. Also, Google and Apple, they know where all the Wi-Fi access points are, because some people leave on their GPS and their Wi-Fi. And so Google and Apple look at this, and so they now know where every access point is. And so you can, of course, say, I switch off my location and I switch off my Wi-Fi, but even then, Google will, once in a while in Android, switch on the Wi-Fi to see which Wi-Fi networks they can see, and then they know where you are, more or less. So this is, in fact, Google knows better where you are than probably your partner, and they can tell you where you were at every moment of your life, better than anybody else. And they use this, of course, to secure their systems and to stop certain attacks. But that's kind of soft information. So we still use passwords. I don't know. I think last time I counted, I had more than 200. So the end of the password is not there. Of course, passwords are easy to guess because people choose predictable passwords. The biggest problem of passwords is that you send them over a channel. Initially, this channel was, the mainframe was sitting inside a bunker, and the people working on the mainframe, they were sitting in the room next to it, and there was even a window. They were working on a teletype and later on a screen, but they could see more or less the cable from their device to the mainframe. And there was passwords to separate different users on the mainframe. This was a problem, started to be a problem in the beginning of the 70s, because in the 60s, only one person at a time could work on a computer. But then in the 70s, there were more users, and then they had passwords. And then in the 80s, we got LAN networks. So then the passwords started traveling on the LAN, and then we got password traveling on the internet. So the problem with passwords is they can be intercepted, and that means they can also be sent afterwards. So passwords do not guarantee liveliness. In fact, passwords, in my definition, do not provide entity authentication, because you check indeed something only known to Alice, but it could have been sent much earlier and replayed later. So password by itself doesn't prove liveliness, and is actually not sufficient. Also, Bob has Alice's secret. So if you want to get passwords, what you do is you offer a great service on the internet, whatever, I will optimize your machine, I will give you beautiful screensavers or a new game. You just ask that the users make a username and password, an account, and what you then do is you start using this username and password everywhere else to see where the user has reused this. So for example, now Google Chrome will tell you which passwords you are reusing, because they look at all your passwords. And Google will never misuse these, of course, or they promise, but they look at all your passwords and they can tell you how many times you reused passwords. There is also the website Have I Been Pwned? You may notice you can find out which of your passwords have been found and so on. But so the core of the problem is that you have to send your password to Bob, and so Bob knows your password. And then, of course, you also need, sometimes Bob is hacked and then all the passwords are leaked. This is even a bigger problem, because then you find out millions of passwords. There have been various attempts to improve passwords, but passwords are very difficult to kill because they kind of work a bit. And all the work is with the user. In fact, for the server side, there is almost no work. Right? You just have to have a mechanism where you have a list of usernames and passwords, and every time you get a password, you look it up and you said yes or no. There's no work. It's very easy to do. And then what you need is you need some mechanism when people forgot their password. So for this, then you somehow send them a link to their email, so you have a backup thing, and then clicking on this link, they can set a new password. So I mean, it's easy code, right? If you want this, you go to ChatGPT and say, write me some piece of code to manage password, and with recovery, and ChatGPT will produce you the code, and then you can run it, and voila, you're in business. It's very easy, and all the cost is for the users because they have to manage their passwords. And of course, what users do is they use password managers, and some are good and some are not so good, because some store all your passwords in the cloud and then lose them, but that's, happens when you put all your eggs in one basket. So the most important message is there is no liveliness checking of a password. So think of this pensioner again with his pension. If the relatives would have gotten the password, they could have collected the pension forever. Okay. So there is some improvements. So in fact, since the 70s, in most applications, only the hash of the password is stored. Which means that if you break into Bob, you will not find the passwords, but only the hash of the password. And there have been several breaches where only hashes were leaked, so at least this gives you some protection. Of course, if your password is 1, 2, 3, 4, 5, 6, your password is not going to help you. Okay, but if your password is reasonably complex, then it will be hard to recover it from this list. So this solves one problem, namely the secure storage of your password, because somehow it is now stored in a secure way, and the cost of this is very low for Bob. Now, the big problem is that computers have gotten faster, still a factor 2 every 18 months, but in fact, our brain doesn't get better. So, a 40-bit password in the 70s was still okay. Doing a 40-bit key search in the 70s was hard. With a 40-bit password, it means lowercase 9 characters, okay? Or it means mixed case and digits, 7 characters, but this is already very hard to remember. So in fact, if you remember my advice on key lengths, we should have at least 80-bit keys. Well, you can't remember this, okay? So if you have the full keyboard, 10 characters, then you get up to 64 key bits, which is not enough. And so this is kind of unrememberable anyway, because it also means Control-C, and which will hang up your connection or close your program and so on. So it actually doesn't work even to do this. What does work is longer passphrases, or if you combine multiple words, that is slightly better, then you can get to 80 bits. But then you have to type these things. So if you can type well, this is okay, but then on a smartphone, this is a disaster, right? Now, there is further improvements. So people propose then, one of the things that is being done in most password systems, but not all, and you would wonder whether the NSA has something to do with this. So a very good trick is to give every user a different one-way function. Because if you look at the normal scenario, when everybody has the same one-way function, if there is 2 users that choose the password, say Gandalf, then they have the same hash value. And so you can even see this in the system. And it's really a problem because you want to avoid that. Also, if you want to recover passwords, if everybody has the same function, remember I explained this to you before, in the last lecture of October. If you have multiple targets to hit, if there is T targets, it's T times easier to hit a target. The ping pong ball story. So in fact, if you have a database with 1 million hashed passwords, finding one password there is a lot easier than finding a specific password, because you have 1 million times more chance every time to find one. Now you can solve this easily by salting, which means you give every user a public parameter, the salt, and this parameter is in green, so it's not secret, so it's just a random string, which you hash together with the password, and which you store together with the password. So it's not secret, it's green, it's known. There is no, you can hide it, but there's no reason to hide it. This means that now every user has a different hash function, which means that if 2 users have the same password, they still will have a different hash value. So you can't see it. And if you have a database with hashed passwords, you have to recover every password one by one. You can't gain this factor. So this is a good improvement and kind of easy to implement. So the more amazing part is that there is still many service providers not doing this, which is really, really bizarre, because it's really no cost. The only thing you have to do is generate 128 random bits when you make a user account. But still some service providers don't do this. So things get a bit better. So you see there is quite some efforts to improve things because passwords are cheap, but of course we don't really want to fundamentally change the economics. So here is the first password hashing function ever invented. It was proposed for Unix in the 1970s, late 1970s. So the idea was to use DES, you encrypt the all zero string, you use your password as the key, and you encrypt 25 times, and this is the hashed password. Okay? So it's a one-way function. Why 25 times? To make it slower. This means if you have a hashed password base, you should also imagine that DES was designed for hardware, and we found later good tricks to implement DES faster. But at the time in the 70s, nobody knew how to do DES efficiently in software. So it was very slow. And then the SALT is a 12-bit modification to DES, which is really not big enough. So only 4,000 users. But you should again go back to the 70s, and then computers had maybe 4 users or 8 users. But nobody could imagine there would be a cloud infrastructure with billions of users. So of course, you still now get many, in a modern infrastructure, you still get many users with the same SALT, so it doesn't really defeat this. So your password is a DES key, so we know you can break DES keys. But of course, in the beginning, it took about a second to check a password. So running this on a computer in the 80s took a second to check a password. So even if you had the hashed password database, you could run to a dictionary of 1 million words, it would still take you 1 million seconds, which is not that long. It's like 10 days, 2 weeks, but still, it would take you some time. Of course, today, you can probably do 40 or 60, maybe 80 or 100 million passwords per second because computers have gotten a lot faster. We have much better DES code. So in fact, it doesn't help. Plus, there is a trick which I explain in advanced cryptography called time-memory trade-offs. You can actually do once a computation for every SALT. You store about 2 terabytes per SALT. And then you can find that every password in time 2 to the 38. But of course, most people don't have 56-bit keys, so probably they have 40-bit keys. So in fact, you can find keys in microseconds. And I keep telling about this in the whole 90s. And finally, a guy, Philip Ursulin, actually made a company. And I had a meeting with him a couple of weeks ago. His company is doing very well. So he recovers for you Excel passwords and Windows passwords and whatever passwords for your Bitcoins and whatever. So he does his computations once. So he makes a big investment, and then he can very quickly, in a matter of milliseconds or seconds, recover your password. And he charged, of course, money for it to make up. So I kept telling this business idea in the 90s, but no student did it, and in the end, a Swiss student did it. And he did very well. So this is what these online services do. This is, of course, also what the NSA does. The NSA has done these computations, and so even if you think your password function is okay, the NSA has done a pre-computation, and they can find any password in microseconds. Okay, more or less in real time. If they have the hashed password, you have no security. So what can you do against this? Well, you can make your password function slower. So in fact, what you can do is, rather than applying the function 25 times, today you could say, I'm applying my function, I choose a more complex function, and I apply it 100 million times. And then, of course, it may take again a second to check a password. And then, even if your hash password database leaks, in fact, it's quite hard for the opponents to find the passwords. They can do it, but you can really put the bar higher and maybe high enough. It's also very nice because every 2 years, you can increase this number. You can take all your hashed passwords and hash them a bit more, twice as much. And then the user doesn't notice this, but you can keep updating your system and keeping it more secure. So this is nice. But of course, then the next step is that the bad guys are using hardware crackers. So they build special hardware with FPGAs to speed up their stuff as well. So then there was a competition a couple of years ago called the slow password hashing competition. So the goal was to design functions which you cannot speed up with hardware. And this is actually very tricky, but more or less what you do is you have a complex function that requires a large memory and that random access in the memory, which is very expensive because a memory access on a full-scale memory of a gigabyte costs about 100 to 150 cycles. And if your algorithm needs many of those, well, there is no way you can build efficient hardware to do this. So this competition came a function called Argon 2, and also Balloon, but in fact, many people still use the older versions, which can to some extent be sped up with hardware like scrypt, bcrypt, pkbdf2, and so on. So there is still quite some of those in use as well. Now, of course, the internet companies don't like this, because if you are Meta or Google or whatever, one of those companies, Microsoft, at any moment there is 10,000 of users logging in. And if you have to then do billions of hashes, so for a second for every user. That means you have to have a server for every user. And they don't like this. So in fact, they don't do this because it's too expensive. It would be a good solution, but it doesn't work. The other thing you have to warn you for is that a nice thing of the Unix mechanism or Linux mechanism, so this, what you could do is you take your etc. pass.wd file and copy it to all your machines. Okay? So if you use this mechanism and you're going to copy it to your Raspberry Pi, then logging in on Raspberry Pi may take 2 days. Because, right, of course, this Raspberry Pi doesn't have this capability. And so you cannot share passwords on embedded devices with this because you can never log in. It takes just ages. So it's a bit tricky. I saw a talk 5 or 6 years ago by Facebook. It's a very, they were called Facebook at the time. So it's very interesting because it gives you a very good idea how security really works in industry. Okay? So what you see very often in security is called bricolage. So you get these nice schemes, but in fact there is legacy. And of course a startup starts from scratch, but if a company exists for 10 years, then there is legacy upon legacy upon legacy, and so more or less the ICT industry is just a spaghetti of legacy. Okay? And so what Facebook did was what everybody else did, was you hash your password with MD5. What's wrong with MD5 anyway? It's fast, cheap, so they hashed with MD5, and they used a salt, which is good. And then they realized it was not good enough, so then they actually hashed with HMAC. So they decided to what we call a pepper. So in fact, they have a special server with a key. And so they actually hash with HMAC, so only on this server can you do the thing. Of course, they have multiple copies of these keys and multiple servers for redundancy. But so the idea is that there is no reason why you would make this key public, and you have a special server, and hopefully backups where you hash with a key. Then at some moment, I guess they were worried that this key would be compromised, and then they still had some very easy to crack password function. So they decided to implement bcrypt. Okay, bcrypt is a slow password hash function. But bcrypt is a problem, but the result is very big. So then they used SHA-2 to this thing to actually make it shorter. So this is the situation 5 years ago. I can bet with you that probably they've added another function in the meantime. So now is the quiz question, why did they not start over? So why do they keep all the old functions? That's a good question. You could say, you come there as a new researcher, you say, I went to a class, and I found out that, Argon 2 is much better. Let's just do all the hashing with Argon 2 and throw out all this legacy crap. Well, it's very simple. The value of Facebook or Meta is in the number of users, the stock value. Of course, number of active users, but also by the number of users. Now, if you send an email to all your users and say, we changed our password system, please log in again because we're going to rehash your password, then you will lose about 30% of your users who never bother to log in again. So, and then it will be obvious to the stock market that you don't have those users, and your stock value will go down. So if you as an engineer come and propose this idea, you will be kicked out, right? You will be. So what do they do? Rather than asking the user to log in again and checking the password with the old way and then hashing it again, what they actually do is they just hash the previous values, and they can do this because the user will not notice. So you can keep changing your system, and the user doesn't notice that something has happened. But of course, you can never change this. So this is how you end up with legacy. And this is how most of security works in the real world. That's why I'm in academia, because I don't like spaghetti, at least in system design. Okay, so can we do better? Yes, we can do better. Today, we can actually store lots of information. In the past, actually, even from the 80s, in the 80s, bank cards got a MAC stripe on the back. They still have a MAC stripe. Your bank card has a MAC stripe. And it's a bit unreliable. So if you hold a magnet to it, it will disappear. But it's actually very easy to use technology, and you can write 135 bytes on this. There is 3 tracks, and the biggest track has 135 bytes. So you can actually write a long secret key on there. And in fact, today, it contains an encryption of your PIN code. So that's even... At least if you end up in a country where they still haven't managed to read chips on cards, then they can actually check your PIN code because it's encrypted on the MAC stripe. And so they can take your PIN code and the encryption and send it to the network, and it will go to your bank, and the bank will check whether this PIN code and encryption match. So it's actually very nice. And then 20 years ago, it got USB keys, so you can now store terabytes of key. So in fact, why should we actually have a password if we can write a long key on some device and carry it with us? So, of course, this is good, but now you shift the problem to the card or the key. If you now lose this USB key, and I find it on the parking lot, or I steal it from your pocket, well, then I can break in. So kind of, yes, this is better than a password, but if you then lose the device, it's actually worse than a password. So another technique, which actually is used in passports, is to write a certificate on your device. What is a certificate? We explained this in lecture 2. A certificate is, in general, it's a signature of a third party on your name and your public key. But in fact, here, it's just a certificate on your name. So it's a very simple statement. It's a statement that has a name, that has a serial number, a validity period. I guess I should update this to 2024, because otherwise it's a negative validity period. That's a bug on the slide. And then you can revoke things, and it says who issued this. So in fact, it's just a statement to say this person is part of the system. Okay? And this is signed with the private key of the government or of the bank. And so this is presented to the terminal or to the border agent, and they only have to apply the public key of the government or the public key of the bank and check, okay, this is a valid person in the system. Okay. So instead of having a key, you have a signature of a third party with a private key, and it just signs that you're part of the system. How do you check this? With the public key of the CA, so it can be the bank or the government. And so, for example, if you have a passport, most of you, or many of you do, there is actually a chip symbol on them, because after 9/11, the Americans forced us to have electronic passports. The Americans don't have it, but we all have to have it to go to the US. And without such a passport, you can't enter the US anymore without a visa. You have to go through a special process. And so this passport actually says this person is a Belgian citizen. It signs your name, your birth date, and your photo and your fingerprints. So more or less that's what's happening, so it kind of identifies you. And the Americans can read this out. They can apply the public key of the Kingdom of Belgium, and then they can check indeed this is correct information. So this is very nice because it makes it harder to forge passports, because of course you can still try to tamper with the photo on the passport, but you can't put a new photo in the chip because this is signed by the Belgian government. So the CIA finds this very annoying because it's much harder for them now to forge Belgian passports. They now have to come to Belgium and say, can you please give us the following forged Belgian passports? Because they need this key now. Right? So this is very annoying for them, but for the rest it's much more secure. Of course, if you think a bit about it, it's not super secure because you can just take a passport and read out this string and write it on a different passport. Now, it's a bit more tricky because to read out the passport, you can do it contactlessly, but you need to open it and use the machine-readable string. This is actually used as part of information to get access, so you can't read the passport remotely without opening the passport, more or less. Or you have to guess a lot of information before you can do it. But so if somebody gives you their passport, you can just take this, especially if you can open it, you just read the string, you use the protocol, and you read out the signature, and now you write it on your own passport. Okay, and so if you're lucky, the border guard will not notice this, that the photo he gets from the signature is slightly different from the photo on the passport, and then you may get away with it. Same thing happened in the financial sector. So it was decided to use public key technology in credit cards, so you could pay everywhere in the world. And this was conceived 30 years ago when there was no internet connections everywhere. And so the idea was that you should show up with your credit card and that your card could be checked by any Coke machine in the outback of Australia and could indeed check that this is a valid credit card without going online to your bank and checking this. And so as we will see, a protocol was developed where you would sign something, but there was also a cheaper variant of the protocol where you just had this kind of signed statement on your card. And that would be enough to, it could be checked by the terminal. So the terminal has the public key of Visa, say, and they could check this and say, oh, this is a legitimate card number. It's not somebody made up a credit card number. It's a real card number by Visa. So I still remember I wrote a report for Europay, MasterCard, and Visa and say, don't do this. Because people are going to put card readers in shops. They're going to read these things and write it on different cards and then use it to do fraud. So the most of the world listened to us except for the UK. So the UK, we told them don't do this because fraud is going to happen. But the UK said yes, but these chip cards with static signatures they cost only 20 cents, and the ones with RSA signatures cost €1 or £1. So we're not going to do this because we have in the UK 20 or 30 million cards, and so this is a bill of several tens of millions of pounds. We're not going to pay that. And so they rolled out this system, and guess what happened a few years later? They had to change the system because people copied this string to other cards and actually made fraudulent payments. And I was not involved in the attack. I just warned them for it. Okay, so before we break, we'll show you what you should do to get authentication. It was invented during World War II to identify planes. So there was the Battle of the Atlantic above our heads here. So planes were flying to Germany to bomb, and the Germans tried to go to the UK to bomb. And so one important question is, do you shoot down a plane or not? And so you don't want to shoot down your own plane, but you want to shoot down the planes of the other guy. So what was invented was a protocol called challenge response. So more or less you have a key, in this case, in the ground station, and one in the plane, and you ask a question, a random question, and then you get a MAC as an answer, as a function of the key and the random number. And if the MAC is correct, then you don't shoot the plane. And if not, you shoot the plane. Or if you make a payment today, or if you authenticate, in fact, you get a random number from the server and you send the MAC back. This is a standard way of authentication. So you have in every card that follows this ISO standard 7816, there is a command internal authenticate. And what you do there is you send a random number to the card, and the card will compute a MAC. In fact, it will encrypt this random number, which is a MAC, and then you can check this. So this kind of solves the problem because every time there is now a new random number. So if you intercept the communication, next time the random number will be different, and you can't reuse this. Okay. Of course, you see that you still need a secret key in your card or in your device, and you have to have the secret key in Bob's database. And so there was a company called RSA, which are called after the inventors. In fact, but the technology came from Secure ID. This was more or less very hot technologies. I think it disappeared about 10 years ago. But if you worked for a company, you had actually a device like this, and you could use it to log in. So other than a password. And what happened was that, so somebody sent an email to an employee in this company, RSA. This happened 11 years ago. With as the subject vacation planning, so the employee clicked on it, and this email had malware, and in the end, this malware took control of the system and stole all their private keys. So this company had to issue tens of millions of new of those devices, and there were many defense contractors using this stuff. Okay, so that's the risk of this approach, that you have all your keys in one place. And so I know it's actually more than 10 years ago because there was not too much information, but I think somebody wrote an article a year ago saying now my NDA, my confidentiality agreement of 10 years has expired. I can now give you the full details of the attack and what actually happened. But so also every bank has such a database of keys, and every mobile operator has such a database of keys. So it's a nightmare because if you lose those keys, then you have a big problem. But the protocol is very nice and interesting. So there is even IETF standard, hash-based one-time passwords. It's called one-time passwords. So, of course, if I think of a Mac myself, I would say send a 64-bit value, right? That's secure enough, or maybe 80-bit value. But of course, if you have to tell the user to type something, people don't want to type this, right? I mean, you know that 20 bits is 6 digits, so an 80-bit Mac, that's 24 digits. If you ask your user to type 24 digits, they will hate you. Okay, so the banks, what they do is typically 8 digits, some banks even 6. So in fact, people use this mechanism, but because it has to be typed by the user, they have a Mac of 6 to 8 digits. Okay, and 10 to the 6, that's a million, that's 20-bit value, and 8, that's something like 24 million value, so that's a 22-bit key. That's more or less what users can deal with. Or it's a bit more, sorry, but in any case, it's like less than 30 bits of Mac. So one of the attacks you can do, of course, is you can keep, even if you don't have the key, you can get a random number and you can send a random value and keep trying, and after 1,000,000 times you will be in. Okay? So what you then do is that here you put a counter and you say for every account you can only try 10 times and then we'll double the time. That's okay, but of course if there is 1,000,000 users, I can still try to log in for each of the users. So it actually doesn't stop the problem. I mean, 6 digits is not enough. Okay, we have to get rid of this. But companies like this system because, of course, today these things, these devices and these cards, they're painful to deal with. You have to mail them and whatever. Today, of course, this is just an app on the mobile phone. So Google has this, Microsoft has this. All these companies have just an app on the phone. The big problem is there is a key in there. And if somebody finds the key, then you're gone. Right? But that's more or less what is being done. Okay, so after the break, we'll look at a small variant of this. We'll use the clock, and then we'll show also how you can improve this with public key technology. And after the break, I will also tell something about the presentations, because the information will be available this week.